All right. Good afternoon. Can you hear me? I would like to start. Good afternoon. Please allow me to start. Welcome back. Um, our second lecture on syntactic analysis. Two more to come, not counting today's. At this point, we're about half a session behind the schedule that we had originally anticipated. Since we used some time on quizzes and the midway evaluation last week. That's not a problem because we had left one slot as a buffer of error, and I've now updated the course schedule, and we'll sort of run over into that pre-final lecture 3 weeks from now, I think, and wrap up parsing syntactic analysis that day, and then I have one more quiz, including bonus points. And then the final lecture of the term will be devoted to exam preparations. So you should find that on the course website. To make good progress today, I don't have much in terms of reviewing from last week. We used about half an hour on the midway evaluation, then complemented the Viterbi algorithm for hidden Markov models with the forward algorithm, in a sense a minor variant. But many of you found it hard to pinpoint the exact differences in the quiz. It's kind of disconcerting. I felt I had told you the answer, like 15 minutes before that quiz question, and still many of you, the majority even, found it difficult to give us the 2 bits of information that we were asking for. It's sum rather than max, and it's computing the likelihood of the sequence over all possible state sequences. Speaking of the quiz, over the weekend I posted my assessment of points. It turned out that I had originally expected to give you up to 2 bonus points, half a point per question. Devilry doesn't allow half points. I think maybe it used to, but maybe it never did. So I inflated the available points for the quiz to 4. And so if you look at your results, whatever you scored, I think the maximum were 3 actually. Many people are at 1 or 2. We'll do the quiz exercise again. It's, from my point of view, primary purpose is to give you some idea of where you stand in respect to the most recent lectures. And then we started to introduce syntactic structure or formal grammar, and that's where we pick up today. We'll formalize this notion of context-free grammar that is intuitive, known to many of you in one way or another. Then we'll talk about training material for supervised machine learning of formal grammars and attaching probabilities to the rules of context-free grammar. And then we'll start to talk about algorithms. In a sense, quite parallel to what we've been doing in recent weeks. And I'll introduce a naive parsing algorithm, at least naive for parsing natural languages. It's actually a fairly common algorithm in parsing programming languages. And then from there, we'll move on and introduce dynamic programming techniques again, because it turns out natural language parsing is a large, complex search problem. So a relatively sort of common approach, I would say, in a new space, predicting hierarchical structures. So to motivate these, no, actually, before we do that, I was going to come back to this question, but now Elena is actually not here. I think some members from her group, where there was a heated discussion last week, how to actually interpret the question, what's the probability of the bigram language technology in this text. Since I had put language modeling into the caption, I would argue there was it was pretty clear how to interpret it. But I think the comment that was made is that you could interpret it either as the probability of the word technology following right after the word language, which we formalize as the conditional probability of technology given language, or the bigram, the juxtaposition of language and technology occurring somewhere in the text, which it was said would correspond to the joint probability of language and technology. It occurred to me, principle one could also maybe try on this interpretation, that language occurs somewhere and technology occurs somewhere. But I think that would not be compatible with the form of the question. Could someone help me make that argument? Why is this not an interpretation of, a faithful interpretation of the question? The question is, what's the probability of the bigram language technology? When they are allowed to occur anywhere, then it's not a bigram, because bigram means they follow each other. So we can take that off the table. And still so here I was using the shorthand notation, events A and B, and left it to our intuitions or joint understanding of what the events actually are. And we can make them explicit. And really what we mean here is, in both interpretations, that the event A is that some word at position I minus 1 is language, and that another word at position I, that's the same I for across these two events A and B, is technology. So this way I actually make explicit that they stand next to each other, because this interpretation up here one could also call a joint probability, the probability of the two words occurring jointly somewhere in the text. But often in the language modeling space we have interpreted joint probabilities actually in this manner, as the sequence of A and B occurring as a bigram. And we had initially related joint probabilities to the product of either A occurring and then B occurring given A, or inversely P of B times P of A given B. That's symmetric. We actually used that symmetry to derive Bayes' theorem. And so from that we could now compute one way or another. And I was going to say, sort of in terms of interpreting the question, if the heading language model wasn't enough of a cue to pick the first interpretation, I think this equivalence might be, because here you actually only need to compute one of the two terms, and hence always pick the interpretation that makes your work less and is defensible. And alternatively, going back to how we introduced basics of probability, I could also define the second interpretation as a complex event. I could say I define an event A where there are two words in the picture, and one is language and the other one immediately after it is technology. And now I can count the size of my sample space, all bigrams, count the number of occurrences, and I can compute this probability directly, or I can derive it from this equation. All right, then let me move on. So we introduced this notion of constituents or constituency, grouping words together that behave jointly. And we briefly gave you 3 constituency tests. I can substitute constituents of the same category in a syntactic context. I can coordinate them, so that was I wanted to read a good book. I wanted to read a good book about probability theory. I wanted to read a book. I wanted to read it. These are all constituents of type noun phrase. They can be coordinated constituents. I think we had the example, I bought a book, took the tram, and read it at home. 3 constituents of type verb phrase because they share one subject. It's I who did all of that. So that's the coordination test. And they can be moved within a sentence. Actually, here I have the examples. I'm sorry. So Kim read a book, gave it to Sandy, and left. 3 VPs coordinated. Or I've moderately modified my moving things around example because I find this more natural. Interesting books about grammar is something of type NP. I can move that to the front of the sentence. That's called topicalization. So ordinarily the unmarked, the standard form of an English sentence would be subject, verb, object. I like interesting books about grammar. But as a constituency test, anything that I can move into that position preceding the subject in English has to be a constituent, because I can only take one group of things and move them there. So that's the notion of constituency that will be central to our formalizing the grammar of natural languages in terms of grouping things. I also motivated grammar as a big building block in computational systems, programs that can make sense of natural language, of human language, because grammar is what determines grammaticality, and ungrammatical strings can be unnatural, or they can actually be very difficult for us to interpret. So Kim was happy because her passed the exam. That's not English. We can kind of work out what I mean, but we need knowledge about the grammar of English to avoid outputting ungrammatical strings. In terms of actually making sense of language, we've repeatedly talked about ambiguity, different ways of interpreting natural language. That's the property that sets natural languages apart from most formal languages. Programming languages better have one unique interpretation. You might think, why hasn't evolution given us natural languages that work that way? Then there would be no misunderstanding. So ambiguity, of course, means that there's room for multiple different interpretations, and often, or at times, speakers will intend one and hearers will perceive another one. So wouldn't it be better if we had a unique word for every concept and a unique syntactic structure for every relation that we want to establish between concepts? If we think of that as a coding problem, then that would be a very inefficient code. So natural language ambiguity actually is a key property. So in simulation experiments, linguists have actually studied the function of ambiguity. And ambiguity means that we can use a comparatively small code to talk about a massive and a massively complex space, our world, a dynamically changing space. And hence, it's actually been demonstrated that evolution of natural languages do evolve, they change, they have co-evolved with us, actually favors certain degrees of ambiguity. It's a balancing act. And humans are actually very good at sort of looking at each other and working out which interpretations grammar maybe admits, but also taking into account what we know about the world, what we know about the speaker, what we know about the situation, sometimes what we want to hear, of course. We often hear what we want to hear. And to us, ambiguity actually is not a big problem ordinarily. To computers, that's the main challenge in dealing with natural language, because ambiguity means search. And computers don't have access to the same kind of world knowledge, the same kind of reasoning that we have available. So, grammars make explicit structural ambiguities. I like to eat sushi with chopsticks or tuna. We've talked about that often. I asked you to try to work out how many readings there are for have her report on my desk by Friday. Any guesses? Or at least any suggestions where the ambiguity, what do you think that means? Have her report on my desk. Let's drop Friday. What am I asking you to do? So it can be a noun or a verb, it can be the written document, or it can be the activity of reporting. Okay? So you're not taking a stand on what that means because I'm not giving you context. And okay, I think you're observing that report on my desk actually can mean two different things. Report is the kind of noun or verb that can take essentially objects in the form of on something. So that's the object, the topic of the report, what the report is about. But on, of course, can also mean sort of located somewhere above the surface of something. I think that's, if we were to spell out the semantics of on. So if we pick the reading where we're asking someone to see to it that some woman does some reporting, have her do the reporting, then that could mean have her do the reporting on the topic of my desk, or have her climb up on my desk and report from there. One is, again, much more plausible than the other. Both are grammatically possible. And the same goes for the written object. So have her report on my desk could be a manager saying to a colleague, I want that written document. Please see to it that it occurs on my desk. So cause the document to come into that location on my desk. If I say have some ice cream at the corner, then I'm not asking you to see to it that there is ice cream in that location at the corner. I'm actually asking you to have in a different sense, in a sense of possession, of consuming some ice cream. So have is also ambiguous. And ambiguity, of course, that's the point of this example, multiplies. I thought I was going to give you a quick, since in the halfway evaluation you asked about actual systems. This is a research system that we have co-developed here in our research group, where there is a large grammar of English, and you can make it take a sentence at a time, have her report on my desk, and inspect the different analyses. And I had asked for up to 5. Apparently there are more than 5, or there are at least 5. So let's ask for a few more. And according to this grammar, there are 6 different readings. And if we squint, we will see that in some report is a verb, in others it's a noun. Her can be a determiner or a pronoun, an NP. So these are the syntax trees drawn in somewhat old-fashioned HTML mode, pre-SVG. And here we actually see that there is something that is very hard for us to read, but this is a kind of first-order logical form. That's a representation of meaning associated to each reading. And so here, for example, we see that let's not get lost here. No, I can maybe post, so erg.delphin.net, I can maybe post the link on the course page and you can go play yourselves. So at least 6 without the Friday, and the Friday will only make it more interesting. In fact, I think there were some missing. I was expecting 12. Maybe I'll go look at that in the break. Finally, speaking of mapping into representations of meaning, something that computers actually can reason with, or that they can execute as queries. Here are three different, syntactically different forms, or syntactically different sentences. They all obviously mean the same thing. So we would expect that at the level of logic, they all map to the same three participant relation, giving between Kim, Sandy, and that book, and that all variants arrive at the same assignment of argument positions in that relation. So let's look a little more at how that works. Still motivating syntax to construct semantics in application to natural languages, but I'll try to be brief so that we actually get to the algorithms. So assume that none of us knows any Spanish. And here we're told something about the grammar of Spanish. And what we're told is that we can group things and call them S. That probably means sentence. When I find the sequence of something called NP followed by something called VP. And I can group a sequence of something called V followed by NP and call that thing VP. So these are essentially grouping rules. They form constituents. Down here I have a different kind of rule, where on the right hand side I have just strings, and these look like words of Spanish to me. And now here are the two types highlighted. Now, given a sentence of Spanish, Juan amó nieve en Oslo, I can apply the rules of the grammar to build a tree, a parse tree. And I can observe in the tree that for each subtree, there's going to be one grouping rule where the mother node in the tree is labeled with the left-hand side, and the sequence of daughters is labeled with the categories from the right-hand side. So this is how this grammar licenses this tree. Here is another instance, a subtree that was built from this rule. Okay, what have I accomplished? I have confirmed that this appears to be a sentence of Spanish, assuming this is a good grammar of Spanish. A good start, but we still have no idea what it means. Here's another one. And here finally are the leaves. So I'm walking you through the complete tree and reminding you of how the pieces correspond to the grammar. Now, to actually approximate what this string might mean, we need to pair the rules of syntax with rules of interpretation or of semantic construction. And for some of them, they will be very simple. We'll just say that the meaning of nieve is something that I call snow. That's a concept. It happens to have an English name. I might find it in some ontology, or could map it to Wikipedia. But it's an abstract thing. It encodes everything there is to the concept snow. And the meaning of Juan and Oslo are just constants that name entities out there in the real world. Now, amo has a more interesting semantics. It says lambda b, lambda a, adore ab. That's a function that is looking for two arguments, and that will insert its b argument into the second position and its a argument into the first position of this two-place relation. And the relation again has a name where I pick an abstract symbol that looks like an English word. And the same is true for the semantics of n. That is also looking for two arguments and puts them into a two-place relation that is called in. And the semantics of these grouping rules up here looks a lot like calling a function. So what this means is whenever I combine P with an NP, I want the semantics associated with the P to be a function to which I give the semantics associated with the NP as one argument. So here I see that P actually is a two-place function. It's looking for two arguments. So it needs to be possible to consume arguments one at a time and have partially applied functions. Okay, so that's the basic idea of semantic construction or meaning composition of a syntax tree. And now we can replace, that's the same tree, but now I'm showing you, rather than the syntactic categories, the pieces of semantics. So here at the leaves of the tree, I've just inserted the terms from the grammar. For example, a door is that two-place function, and the semantics of, the semantics of amo is that two-place function. The semantics of nieve is this constant. And when I use this rule, I want function application of the semantics of the verb to the semantics of the NP. So snow becomes the first argument that the function is looking for. So lambda b, lambda a means I'm looking for two arguments. I can bind one that leaves me with a function that's looking for one more argument and has the argument that is actually instantiated here inserted into the position of the b. So I have bound one variable. And I continue doing so. So here I have the same for n Oslo. First it gives me one argument and leaves me with a function that's looking for one more variable. And now I can combine VP followed by a PP to another VP. Do I have that here? No, I don't. So that's here. VP followed by PP becomes VP. And the PP is the function. So I take this term, looking for one variable, and plug in this term. The C gets bound, saturated, but this is actually a partially instantiated function. It's still looking for one argument. It continues to look for one argument. So all of the lambdas get accumulated at the front. They account for the missing pieces, essentially. And that effectively means that the adoring by A of snow is now embedded in the two-place in relation, in Oslo, which we can interpret as in the location of. Finally, when I combine this with the subject NP, I fill the last remaining argument position, and I end up with a logical term that says John adored snow. There was some adoring holding between John and snow, a two-place relation. And that thing is embedded in Oslo. So that happened in Oslo. So this is how this simple grammar with very simplified, a formal semanticist like my colleague Jan Tore Learning, I think wouldn't be able to present it at this level of simplification. We're taking many shortcuts here, but the basic idea is that I can put the pieces together one at a time and arrive at a kind of first order logical term that I can now interpret, assuming I know how to interpret the building blocks, the concepts. So we have, in a sense, translated a sentence of Spanish into a logical representation, where we have conveniently labeled the relation symbols and the constants using words of English, concept names. But wait a minute, that's the kind of sentence that I think already makes you expect there's something, there's ambiguity here. So, John adores snow in Oslo would be the way of saying that in English. Is there another way of interpreting it? Kim ate sushi with tuna. I saw an astronomer with a telescope. There you go, we have television. Jon, a Norwegian, unfortunately happened to be in Spain when the snow came. And of course he sort of couldn't leave the television, just had to watch snow falling in Oslo. So that's another interpretation. And we already kind of know that we want syntactic structures to correspond to differences in interpretation. So here we will group snow with in Oslo. If you look at the tree shape, here we grouped adore snow in Oslo, the verb phrase. Here we group the noun phrase with in Oslo. So the constituent structure is different. The in Oslo either attaches to the snow or to the adoring. And we get a corresponding effect in the semantics, because now the outermost term is adore by John of snow in Oslo. So the difference in syntactic structure projects into different nesting in the abstract logical representation of meaning. So that's the main motivation for us in that's among the main motivations in natural language processing, where we want to enable computers to make sense of language to do syntactic analysis. I sort of backed out saying the main because there are other natural language processing problems where syntax is enough. For example, grammar correction. So the Office grammar checker doesn't care about the meaning of what you write, but it cares reasonably deeply about the syntactic structure. All right, so that's the motivation. Finally, let's formalize it. We'll formalize it as context-free grammars, or CFGs, formal system that models constituent structure. It's built around this notion of grouping and hierarchical embedding. We define it in terms of two components, the lexicon and the set of rules, which we both have seen in the grammar of Spanish already. It can be applied to natural languages, that's what we'll be doing, but equally so to programming languages, to protocols, to modeling languages. And in fact, context-free grammars is essentially the formalism behind something that you know well. Bacchus-Nauer form is essentially a notation in the formalism of context-free grammar. And context-free grammars are a big step from the sequences that we have had available so far to model natural language, but they still keep us in a computationally tractable space. And we'll look at that space later today. So semi-mathematically, we'll formalize a CFG as a quadruple, including a set of categories or non-terminal symbols, the names of the groups, the constituent categories, a set of terminal symbols or the vocabulary, the actual words of the language, that's the lexicon. No, sorry, that is not the lexicon. That is just the vocabulary, the inventory of the surface words. A set of category rewrite rules, also called productions, that tell us something about how sequences of categories can be grouped into constituents and what the constituent category will be. And we actually also use the rewrite rules, the productions, to spell out the lexicon. So the lexicon is the pairing of terminal symbols, words from the vocabulary, with their lexical category. So there are two types of rules. Lexical rules, where the right-hand side is a single word of the vocabulary sigma, and syntactic rules, where the right-hand side is any sequence of categories. Finally, the fourth element is the start symbol, essentially an expectation of the category at the root of all well-formed syntactic trees, a filter on complete results. So in this grammar, we're making the simplifying assumption that you can only talk in full sentences. That's of course not true. I will often, in response to a question, just give you a noun phrase. Who just arrived? An old friend. Or a verb phrase. Many of these constituent categories can actually occur as standalone utterances by themselves. But the sentence is the prototypical, that's the complete form of putting things together. All right. Here I have some formal requirement on the format of rules, and we'll use this syntax repeatedly now. So alpha is the left-hand side, rewrites into a sequence beta 1 to beta n. It's the general form of all rules in P, the set of productions, where the left-hand side symbol alpha is a category, it's a non-terminal. I can never have a word on the left-hand side. And beta I comes from the union of categories or, that is non-terminals or terminals. So in principle, I can have rules that mix and match constituent categories and words on their right-hand side. I'm not banning that in this definition. This is the general form of context-free grammar. And initially we'll look at restricted forms, and then we'll move back to the general form. All right, as with our earlier models, we can think of a context-free grammar as a generator of language, and we'll take a top-down view. So for grammar G, we say that it generates a language, L of G, and that's defined as the set of strings that can be derived from the start symbol of G by convention S. And to derive some sequence W1 to n from the start symbol S, we apply the production system, the rewrite rules recursively. We know at the top we need the start symbol S, and we can essentially generate tree structure top down until we have at the leaves only words WI from the vocabulary sigma. So on this view, the grammar generates strings. That's why it's often called generative grammar in formal linguistics. And those strings generated for a given grammar G are those that we call grammatical. They define the language. Everything else is ungrammatical and not part of the language. CFGs are called context-free because other than having the right category for the left-hand side of a rule, there are no conditions on where I can use the rules. I can use a rule, VP goes to VP PP anywhere, everywhere, where the dominating context is looking for a VP. So the rules are, the applicability, the use of each rule is only constrained by its left-hand side. A single symbol, single non-terminal symbol. All right, so that's the formalism, context-free grammars. Probably familiar to some of you from a class like in 2820. Intuitive, I hope, to all of you from your use of Bacchus-Nauer form. Now we have formalized it to an extent that allows us to talk semi-formally about algorithms. But very soon we'll not be interested in all possible trees given a grammar for a string, but we'll again ask, have her report on my desk, well, what's the most probable, what's the likely interpretation? What does that actually mean? And we'll again approach that in terms of probabilities, so we'll want to assign probabilities to our syntax trees. We'll pair a context-free grammar with a probability model over syntactic structures. And to estimate those probabilities, we'll need training data. We're still doing supervised machine learning. And the training data now is a corpus, natural language, paired with syntax trees. And that's what we call a tree bank. So our training data gets increasingly more interesting. For the HMM, we gave you training data that is running text with parts of speech. Now we'll move to running text with complete syntax trees from the same running text. And treebanks usually, well, require some expertise, some infusion use of expert knowledge, manual annotation. And they can be constructed completely, well, manually from the grounds up. So the Penn Treebank that we'll look at soon was constructed by paying doctoral fellows, PhD students at the University of Pennsylvania to write down those trees. And they were trained on the rules of the grammar and the assumptions that they should make, and that was an almost fully manual effort. They had some tools, powerful Emacs macros actually. Another way of constructing a tree bank nowadays might be when you actually have a grammar, like the system I showed you briefly in the online demo, that can give you all of the trees. Then you might ask, isn't it easier to ask an annotator to identify the right tree? But of course, when all of the trees is a large set, and it can be, we'll soon see tens of thousands, even millions, then picking the right tree can also be a difficult proposition, even to graduate students in linguistics. The Penn Treebank is what has dominated much statistical parsing research for the past 20 years. It's about 1 million tokens of Wall Street Journal text. You've seen it already. You're getting used to stock prices and investments and mergers. And it was first annotated with the parts of speech that we're currently using for our tagger implementation. And it was then in a second step manually annotated with somewhat coarse constituent structure. I briefly sort of reflected on the Penn Treebank tag set. I said they differentiate NN from NNS, nouns from plural nouns, because in English you mostly see the plural by an S. And that was a pragmatic decision. A range of distinctions, 45, that they expected annotators can make reliably. And they did the same thing for syntactic annotation. They defined a somewhat simplified notion of the syntax of English and wrote an annotation manual, a handbook to the annotators, and then asked them to write down those trees. Here is one tree from the Penn Treebank. Maybe it doesn't look so coarse to you. Still, Times Move is being received well. That's probably Time Warner in the Wall Street Journal domain. I have no idea which move they took in 1989, so all of the text is from 1 year of the Wall Street Journal. And here we see as the pre-terminals the parts of speech that we already have encountered. And from there things are grouped. The lexical category for still is RB, which means adverb, and then that becomes an adverbial phrase all by itself. Times move becomes an NP. Is being received well becomes a VP. First being received well is a VP, and then is being received well is another VP. So here we see some recursive embedding of categories. And we see some things that we can't quite. So S, NP, VP, we've seen already. We're beginning to get ideas of what these means. But here in the Penn Treebank, these are further annotated with function labels. So this is the subject NP. This is a manner adverbial. It was received in a good manner. And there are some things that we actually don't find in the original string. So here there is something that has a pre-terminal category none. And no actual word down here, but an asterisk and a 1. And that 1 is the same one as the one over there. That's called a trace. So that's because this is a passive construction. And in the passive, the object becomes the subject. I gave Sandy a book. I met Sandy. Sandy was met. So the object of meet, Sandy, in the passive construction becomes the subject. To express the original subject, I can say Sandy was met. Any ideas? I met Sandy. Sandy was met by me. So I can use a prepositional phrase using by to express the deep subject, the original subject. So what the pen treebank here does is it says, well, receive once an object, and that would ordinarily follow oops, the verb. But we actually don't have that. We have a passive sentence where that object is now expressed as the subject, and hence the none here means this is where the object should have gone, and the one means the missing object is actually realized as the subject. Fortunately for us, or unfortunately for the field, some think, it has been far more common to ignore these additional pieces of information in the pen treebank and operate on further simplified, on reduced pen treebank trees, where these empty elements are removed, where the function labels here are removed, and where the co-indexation. Once you take out the empty elements, of course, you no longer need the co-indexation, because there is no missing object notion. And so this is the tree as we'll actually see it, where, well, it looks more accessible, of course. It will be easier to parse because we don't have to worry about empty elements, words that actually are not in the original string, and because the inventory of labels is smaller. There's no NP subsh. On the other hand, we have thrown away some information, so the traces were the empty elements and the function labels. In this tree, it is less straightforward to recognize that this is an instance of the English passive construction, and that what times move is actually the underlying object to receive. Times move is not doing the receiving, as the subject would ordinarily do, but it's what is being received. And once we've thrown away some of the syntactic information, we have made that correspondence to the underlying logical form less accessible. But so far in statistical parsing using the PTB, we have for 20 years been content aiming for syntactic analysis. That's been a difficult enough problem to keep many researchers engaged. And this simplification has enabled the development of reasonably accurate and reasonably efficient algorithms that solve this problem. Let's take a break here and then actually talk about these algorithms. All right, let's move on then. Okay, I was hoping to get to parsing algorithms right after the break, but I had overlooked that there is a missing component. We still need the probabilities over our trees. So we have a tree bank, a collection of trees like this. As before, we want to associate a notion of most likely to a probability distribution over the space of possible trees. And in a fairly straightforward move, we'll derive that by associating probabilities with each rule, with each element of the set P of rewrite rules, the productions in our grammar. And then the probability of the tree at large will be the product, the joint probability of using all of those rules together. So each production rule will have a probability associated to it, and for the set of rules that start in the same left-hand symbol, S in this case, the sum of their probabilities should sum to 1, because the probabilities associated to productions are actually conditional probabilities of generating the right-hand side, the sequence of NP, VP, given the left-hand side, dominating category, context of category S. And as before, these probabilities we can estimate or learn using maximum likelihood estimation from annotated training data. And this is the graphical, more readable representation. This is how the Penn Treebank actually is written down internally. Essentially a Lisp S expression. And they did use Emacs to write those probably poorly paid students, but surely they learned a lot. And in fact, their identity is not really publicly known. But creator of the Penn Treebank, I think would be arguably a call to fame in natural language processing nowadays. So that's the same tree as an S expression. And estimating a probabilistic context-free grammar essentially means reading out rules and, in a first step, counting their frequency. And so reading out rules essentially means every subtree of depth 1. So here I start in the lower left corner of that tree, here, and now I work upwards and cut the tree into subtrees of depth 1 and record how often I actually see that subtree. Here, towards the end, we come to a subtree, there's a typo, add p, that we have seen before. So here we actually increment a count. That's a rule that we already know in the grammar, that in this one training example we actually see twice. I think that's the only rule that has a non-singleton frequency. The backslash period and the vertical bars is just the common Lisp syntax. These are symbols, but because the comma and the period have special meaning, have operator status in Lisp, I need to escape them. And the general procedure for escaping symbols is to enclose them within vertical bars. When I just have a period, one character, then I can also write that as backslash period. I could have written this as vertical bar, period, vertical bar. But this is what the Lisp reader actually makes of it. That's the shorter representation. They are equivalent. So that's comma, that's the period as a Lisp symbol. And once we have the counts, we turn them into probabilities by normalizing according to the conditioning context. And that's the sum of occurrences of the left-hand side symbol. So I've seen, this is now for, this may actually be for the complete Penn Treebank, yeah, I think it is. So there are actually many ways of deriving sentences in English. Many of them start with noun phrases, that will typically be the subject, but some start with adverbial phrases. And then a comma. On Monday, comma, I met an old friend. I have the counts for them, and I normalize to the counts of the conditioning context. How many trees, subtrees of depth 1 are dominated by S. So that's the same procedure. So this is not the complete Penn Treebank because there are many more than 1,000 trees. That's the procedure for assigning probabilities to the rules of the grammar. Straightforward adaptation of things we have now done repeatedly. And in the final assignment, we'll actually ask you to write a statistical PCFG parser and train it on the complete Penn Treebank and test it. So again, we're almost catching up with the state of the art in statistical parsing. And again, the challenge will be to design the data structures and the code so that you can actually deal with a fairly large set of rules, all of the rules that come out of those trees that those UPenn students wrote down for 1 million words of Wall Street Journal text. And well, then putting them together in an efficient parsing algorithm. All right, so now let's talk about parsing. So that all of this was preliminaries. This was getting us ready to talk about parsing algorithms. So now we have a formal model, context-free grammars. We have a probability distribution over that model, PCFGs. We have annotated training data, the Penn Treebank, and very soon we'll also talk about how to evaluate, and then we're ready to experiment. Okay, so let's talk about parsing algorithms, the parsing problem. Here is an English translation of the grammar of Spanish. It would seem that English and Spanish actually are the same language, only the words are different. That's not doing justice to Spanish. But for the purpose of this example, the grammar of Spanish resembles that of English. I've now grouped multiple rules using a disjunction symbol here. So this line actually is 3 rules. VP goes to V, or VP goes to V NP, and so on. And I've reminded us of the notion of the well-formed trees or derivations. A derivation is a sequence of rule applications. And all of the complete derivations given a grammar are rooted in the start symbol. Label internal nodes with categories from the non-terminal set C, and the leaves with words from sigma. And for each subtree, each local subtree of depth 1, they instantiate a grammar rule from the set of productions. And here is our tree. Is there anything missing? Given this grammar, is this a valid tree? He wouldn't have put it on the slide otherwise, unless there's a typo. But you could sort of confirm that by now doing the thing I did using highlighting for Spanish before, justifying every subtree and the leaves against the production symbols. It's certainly rooted in S, so yes, this is a valid tree. Are there more complete derivations according to this definition? Something could go into this white space here. There's another one where I use the rule NP goes to NP PP to combine the in Oslo with snow, whereas here I had used the rule VP goes to VP PP to attach it to the adoring. So the classic, you must at this point think PP attachment ambiguity. Whenever there are prepositional phrases, they can modify either nouns or verbs, and they will usually give us this choice. So watch out for that. Now here's our first naive parsing algorithm. I could essentially do what I said when introducing context-free grammars as a generative process. I could generate trees top-down in a recursive procedure. At each point, I'll assume there is a parsing goal, essentially the current category that I'm expanding. And I'll use the grammar rules to rewrite alpha into a sequence of right-hand side symbols of a given rule, beta 1 to beta n. And then I'll recursively do that for the sequence of right-hand side symbols. So my parsing goal will become beta 1. I'll work on that recursively. Eventually I'll come back to that same context, and my parsing goal will become beta 2. And I'll do that sequentially for all of the right-hand sides of each rule, and recursively for all nested invocations. The rules, the right-hand side symbols, beta I, can be from either the non-terminals or the terminals. So it's perfectly legitimate to hope that my parsing goal on a recursive invocation for beta I is now my current temporary alpha. That's what I'm looking for. And that will eventually become a prefix of the input string. And at that point, I have succeeded in parsing part of my string. I only need to get through the full string to eventually put the results of these recursive calls into a tree structure. That's what I've sketched down here, but I think I'll actually skip that because we are not implementing that algorithm ourselves. But here's the corresponding Lisp code. It's really fairly simple. It's an algorithm in good standing for the parsing of formal languages. It's about this most straightforward algorithm I think you can imagine. But with ambiguous languages, like natural languages, it has certain issues, or it makes, well, the algorithm has certain issues, but it also helps us see the challenge in parsing natural languages. So here I'm constructing an artificial, a subset of English, where I say Commodores snow in Oslo to the n. So n prepositional phrases. You could substitute in other prepositional phrases for in Oslo. On Monday, in the woods, on the mountain, behind the lake, in winter. There's no shortage of prepositional phrases. And for no prepositional phrase, Commodores snow, there's just one reading. We're assuming the current grammar of English, the grammar I had on the preceding slide. And the recursive descent parser makes 46 calls. And Commodores snow in Oslo, we already know there are 2 readings. And Commodores snow in Oslo on Monday, how many readings would you have guessed? We used to actually ask that as an exam question. Given this grammar, write down all of the trees, if any, for Commodores snow in Oslo on Monday. Turned out some students use half an hour on that, because even this much of combinatorics is really not easy to keep straight in our heads. So Commodores snow in Oslo on Monday, that can be Oslo on Monday, or let's say Commodores snow in the forest on the mountain. That's maybe a little more, that will be easier to see some of the ambiguities. Commodores snow, what did I say? In the forest on the mountain. So the second PP can modify the forest, the immediately preceding noun, or it can modify the adoring. It has 2 choices. The first PP also has 2 choices. No, sorry, the Commodores. Well, you see, this can take half an hour. Take it, write down those 5 trees. But there's 5 of them, not 6 as one might expect, because high attachment of the first PP blocks low attachment of the second PP. All right, so the second PP has 3 options. It can modify the noun in the preceding PP. It can modify the object noun, snow, or it can modify the verb. The first PP has 2 choices, so you might think there should be 6 trees, but one of them is structurally not possible, because when the first PP modifies the verb, then the snow, the object noun, is not accessible to the second PP. We cannot have crossing edges in our trees. So that's how we get to 5. It's possible to draw this, but it's not trivial. But it's certainly a worthwhile exercise. I encourage you to draw these 5 trees. We might, after all, go back to asking that as an exam question. Seems unlikely, but could happen. Now, if we increase n, then something dramatic happens. So with only 3 PPs, and there are many sentences in the Penn Treebank that have more than 3 PPs, we're at 14, 42, 132, this is known as the Catalan series. And what we observe is exponential growth. Exponential growth is something that we usually consider intractable in computing, and something that scares us. So natural language has a scary property. I mean, the number of calls grows exponentially. We might hope to make the algorithm better. But the number of distinct trees grows exponentially. That is really a scary property. So, if our goal is to find all trees, then there cannot be an algorithm that has less than exponential complexity, because we cannot enumerate a set of results that grows exponentially in less than exponential time. Fortunately, linguists are sometimes interested in all of the trees. Practical applications never want to consider all possible interpretations. We'll be looking for the most plausible one, or an n-best list, a short number of candidate high probability trees. But keep that in mind. So if we define the parsing problem as I did here, enumerate all complete derivations, then we're in exponential space. So have some respect for that problem. Now a little bit of carving up the space. The recursive descent parser and this idea of a context-free grammar as a generator of strings is a top-down view, or a goal-oriented view. At each point in time, we're looking to prove or to instantiate one category. And it doesn't take much imagination to see that the recursive descent parser will run into an infinite loop for rules where the first element of the right-hand side is the same as the left-hand side. That's a perfectly legitimate rule. We've used it already. PPs can attach to verb phrases, and the result is still a verb phrase. I still don't have the subject. And I can do that any number of times. So this is a perfectly, linguistically, perfectly legitimate rule. But an immediate problem for the recursive descent parser, and conceptually a problem for most top-down algorithms. Practically, the recursive descent parser just generates trees, and it hopes to arrive at the words of the actual string. So it's uninformed by the observable input. It's not taking the actual piece of language that I'm given into account until very late in the process. So that means for a larger grammar, it will hypothesize many unmotivated subtrees, which it will find all have leaf nodes, terminals, words that are actually not there in the string. That seems computationally wasteful, because the actual string, the observable input, is a premium guide in parsing natural language. We will from here on assume bottom up as our basic search strategy, the inverse, the data-oriented parsing, where we essentially start from the string and try to group things. And hoping, in doing so, hope to eventually arrive at an S, a complete tree that covers everything and has the start symbol. You might make the sort of parallel criticism that in the algorithm that I'm about to present, we're, while parsing, not thinking much about the goal of parsing, and that will be S, the start symbol. We're just blindly grouping things in all possible ways, and just hope that at the end of the day we'll be looking at a tree that has the start symbol as its root. So there's an abstractly parallel criticism that could be made to pure bottom-up algorithms. And there are hybrid algorithms that combine top-down and bottom-up elements, or goal-oriented and data-oriented elements. But for natural language parsing, even though we make the simplifying assumption that you can only talk in sentences in English, that is of course not true. What did John do during his trip to Spain? Adore snow. So I can use a verb phrase without the subject as a root level utterance by itself. And so this property of bottom-up parsing can, for some applications at least, actually be desirable. Even availability of partial analyses for prefixes, for substrings, can, for some applications, be a useful property. So we'll be looking primarily, exclusively at bottom-up parsing algorithms. And before we can look at tractable algorithms, or before we can define tractable algorithms, we need to take home what I call a key insight here. Essentially, what will allow us to compute in polynomial time, even though, in a sense, our search space grows exponentially. And the key insight is that often there will be structurally distinct analyses for substrings corresponding to different interpretations, but they will have the same category, and that's what we will call local ambiguity. So there is, for parts of the input, there is ambiguity, but the different ways of analyzing that part of the input all have the same category as their constituent category, as their top node. And that means they are interchangeable, given the context-free assumption we're making, with regard to the rest of the input. So here I'm looking at the example, slightly sexist. I keep saying year after year and still haven't changed it. Boys with no, actually no, this used to be girls with, I think last year I actually made that change. So nothing sexist about this example. Boys with hats from France. Well, boys sexist maybe. And I'm kind of suggesting that this can be part of a larger sentence. For example, I adore boys with hats from France. And what would you expect will be the constituent category for boys with hats from France? What's the head? What kind of thing is that? I adore boys with hats from France, comma, snow, comma, and him. So I coordinated 3 things and all are of the category. What's the constituent category for snow? NP, because snow is a noun. And so in boys with hats from France, we're talking about boys. That's a noun phrase. It just has 2 modifiers. And just as for sushi with eating sushi with tuna, these can be French hats or French boys, if we just use sort of common sense reasoning. And 2 interpretations we will expect to map to 2 different structures. And the structures are hiding in this diagram here, which is often called a forest, a collection of trees. And we can read them out by using the legend up here that tells us edges, or the arcs here, well, let's call them edges. Numbered 1, 2, 3, 6, 7, and 9 are all of constituent category NP. And 4, 5, and 8 are of constituent category PP. So 4 with heads, that's a PP. And the head of that phrase is the preposition with. Same true for 5 and also for 8. So 8 with hats from France, I'm saying, is a PP. What would that entail? that 5, the smaller pp from France, must be somehow embedded in the larger pp8, namely as part of the noun phrase hats from France. So this is the attachment of, well, that corresponds to French hats. Then the from France gets incorporated inside of the object of the first pp of this noun phrase number 7. And using that, pp8 and np1, I have only 2 rules that I'm using here. np goes to np-pp, and pp goes to p-np. These are the 2 rules I instantiate for this little forest here, for this substring. So 1 is an NP, 8 is a PP. What I can read out from this diagram is that NP plus PP can become what? I think you said NP, thank you. And 9 is indeed an NP. So that's one reading. 1 plus 8 becomes 9. And are these the French boys or the French hats? The French hats, because we already observed that in the PP8 from France is part of the NP7, and that means hats from France. We expect there's another reading, because we know we're looking for 2, so where's the other one hiding? Or not hiding? I'm telling you up here. So you know how to read. But can you, so 6 boys with hats, 5 from France. Category of 6 is an NP. Category of 5 is PP. NP followed by PP, I can group together as an NP. And I have only one edge for the entire string here, so that's the key inside. There are 2 different ways of calling this substring an NP. And they correspond to different internal structure. But what matters for parsing this substring as part of a larger sentence is the ability to call from 2 to 7 this substring an NP. For I adore boys with hats from France, to find the structure of that sentence, I don't need to know whether the boys or the hats are French. But those boys will be the object of the adoring, either way. And so in that respect, here we have found local ambiguity. And local ambiguity is defined here. It's more than one way of deriving the same constituent category for the same substring. NP from 2 to 7 in this case. And switching to this diagram-like notation and deciding that I only put one edge of the same category into this forest, I have recorded everything there is to know, but I stop this local ambiguity from cross-multiplying with other ambiguities in the sentence. I bound it or pack it or factor it, common terms that are applied here. So I could have, by naive application of my grammar rules, I could have put another edge 10 into this forest and somehow recorded that 9 corresponds to 8 plus 6, 1 plus 8, I'm sorry, and that 10 corresponds to 6 plus 5. That would be making explicit that would then be 2 trees rather than this packed or factored or bounded forest, where a single entry 9 actually represents two trees that have the same start and end string positions and the same constituent category. That is, that are equivalent in their interaction with other parts of the sentence in a context-free grammar. So that's a very important thing to observe. If this is the first time you're exposed to this, then, well, it's discussed in Jurafsky and Martin. Make sure that you're comfortable with this notion. What is local ambiguity? Common exam question. How do we deal with it? How do we detect it? How do we deal with it? So this diagram here is often called a chart. It represents a collection of trees, hence the playful name parse forest. A single item or edge represents multiple trees. It's the key insight that have the same category. And here is our first algorithm that actually takes advantage of this insight, the Koch-Kasami-Younger or Koch-Younger-Kasami. It was semi-independently actually discovered 3 times by these gentlemen. Who has seen the CKY algorithm before? I think those are the language and communication students. We have here a tabular representation of the same basic idea, a chart, a 2-dimensional table that records category assignments for substrings. And the row indices are start positions into the string, and the column indices are end positions into the string. So Kim adores snow in Oslo is our string. It's actually not on the slide, but you remember it by now. And according to this table, there is an NP from position 0 to position 1. So what does that correspond to in the string? Kim, let's make it slightly more interesting. What does this category assignment correspond to? This cell here, the VP. At row 1, column 3. Kim adores was one proposal. Others? Snow in Oslo. How do we count? If you look back here, first of all, we count the spaces between the words, because these are the vertices in this graph, and the edges correspond to words or constituents. Furthermore, I was assuming here, or suggesting, that this is part of a sentence like, I adore boys. So we count 0-based, and we had observed that 0 to 1 is Kim. That's an NP. And so let's go back to this cell here. 1, 2, 3 corresponds to adores snow. And that is, of course, a verb phrase. It's a verb plus a noun phrase. Doesn't have a subject yet. It's not a sentence. So what we see here is 2-dimensional rendering of the same information we had, slightly more graphical on the preceding slide. That's a parse forest as a table. Where is the complete tree? Kim adores snow in Oslo. We know the grammar by heart. We know it's part of the language, that string. Where is the complete tree in this table? From 0 to 5, and that is which cell? Well, from 0 to 5. That's row 0, column 5. So up here in the upper right corner, so you could turn this, what is it, 90 degrees? 45 degrees, I guess. And then it would actually correspond, and then you could draw the arches, the curves. And then this would be the top edge spanning the entire input. It's just going to be more convenient to view it as a table. Okay, to fill in this matrix, what do we need to do? We need to consider all possible combinations. And one convenient way of doing that is to fill it in one diagonal at a time in a bottom-up manner. So we'll start with these cells, and which length of strings do these cells correspond to? How long are the strings corresponding to these 5 cells here at the bottom diagonal? They're 1. Each of them goes from 0 to 1 or 1 to 2, so these are the actual words. And parsing those is not hard. What can we do? We essentially look at what I call the lexicon, the part of the production system where these words occur on the right-hand side of rules. And then the left-hand side will be the category. Do you recall the grammar? Where is it? Way back. So Kim, Snow, Oslo, all are right-hand sides for NP rules. Adores is a V and in is a P. Let's double check that these are the categories that we have down here. So that's the initialization, the first part of our algorithm here. For I from 0 to the length of the input, put into, so this table I now call the chart, put into position I to I plus 1, all alphas, such that there's a rule alpha goes to input of I in the production system. In this case, there is no lexical ambiguity. All of our words have exactly one category. But note that this is a set metaphor here. So each of the cells can potentially contain more than one category. But it's a set, so we don't want more than one element of the same category, because that's how we get local ambiguity factoring. Okay, so we have computed the first diagonal. Now we need to consider combinations of things. And the next diagonal will correspond to strings of length 2. 0 to 2, 1, 2, 3, and so on. That's still easy, because for length 2, the only pieces I can possibly combine will be 2 things of length 1. We're actually making certain assumptions about the grammar here. We're assuming that all rules are binary. There are exactly 2 categories on the right-hand side. We'll come back to that assumption very soon. So, I ask, can I take, but to use a rule, I need 2 adjacent occurrences of categories that account for that entire substring. So to put something into cell 0 to 2, I would need a rule that says NP followed by V can be grouped. There is no such rule, hence this cell remains empty. V followed by NP, however, I have a rule. I can call that a VP. That goes here. And so on. P followed by NP, that goes here. So what we're doing here is a nesting of 3 variables. One for the increasing length of substrings from no, that's not the increasing, that's the I plus j. No, that is the length of the substring. And then I was asking myself whether this actually should be a grader, but that can't be true, because this is tried and tested. I don't expect any typos in here. So 3 nested loops for substrings of increasing length. I need to consider all combinations of cells that jointly, taken together, account for the length that I'm currently considering at the position that I'm currently considering, which is starting at I and going to the current target position, if you will. The cell that I'm trying to fill is I plus length plus 1, because we're counting interword spaces. So what I've drawn here is how target cells can be filled from combination of smaller cells. So for example, 0 to 2 we just did. There's only 0 to 1 plus 1 to 2 that taken together, if I find a rule that allows me to combine elements from these cells, put something into 0 to 2. For the rightmost corner, 0 to 5, there are actually 4 different combinations that I need to consider. So 0 to 5, I can take something from 0 to 1 together with something from 1 to 5. So this cell and this cell actually together account for the full string. If I were to color code it here on the board, you would hopefully see that. And NP followed by VP, so they don't look adjacent in the table, but this NP and this VP actually are next to each other in the parse forest. NP plus VP, that's something that I can call S. But there are other possible combinations. I can take a cell that accounts for the first 2 words, 0 to 2, and combine it with 2 to 5. So these 2 I also need to consider. I don't know where the split points are. I don't know how long the first constituent should be and where the second constituent should start. But because this cell is empty, there's not going to be anything resulting from this combination, 0 to 2 and 2 to 5. 0 to 3, an even longer prefix, this S, I could in principle combine with 3 to 5, S followed by PP. So both cells actually offer me something, but there's no rule in the grammar that says S followed by PP can be grouped. So that's not going anywhere either. Finally, 0 to 4 and 4 to 5, again an empty combination. So in this case, I need to try all of these pairings, all 4, and consider all elements from each of the 2 cells cross-multiplied against the right-hand sides of my rewrite rules. Oops, we're running out of time here. So let me wrap up. This is exactly what is written down here. I take beta 1 from one chart cell, beta 2 from another chart cell, such that they jointly sum to the current target length and position. And whenever I find a rule alpha that rewrites this sequence of daughter categories, then I union that into the chart cell that I'm currently computing. And this algorithm will print out, or it will go through the diagonals and consider combinations one at a time and work its way towards the upper right corner. Okay, need to stop here. I had one more slide. I'll return to that next week.